of thermodynamics.
The first law says that total matter and energy are conserved. In other words, you can't get something for nothing. There's no free lunch.
So it turns out that the total amount of matter and energy in a system can be neither created nor destroyed. The matter and energy can change forms and they can turn into one another, but the total remains the same. So for example, in this rolled up newspaper, there's a lot of energy stored in the chemical bonds of the paper. But if I ignite the paper, I can activate those bonds and I can start breaking them, and that releases energy in the form of light and heat, which you can see and feel. The total energy content is still the same, but it's being dissipated out into space. And a lot of particulate matter goes off as well, and smoke goes off. But if I were to add up all the smoke and the particulate matter and all the energy that's given off and everything total, I would get exactly the same amount of mass and energy total as I had to begin with. They simply changed forms.
If the total amount of mass and energy remain constant, this seems to imply the universe will always have energy and should last forever. But the second law of thermodynamics crushes this notion.
The second law of thermodynamics is the most curious of all. It says that total amount of disorder or entropy always increases in the universe. In other words, things rust. Things decay. Everything gets old and eventually falls apart and rots. In some sense, the second law is a death warrant. A death warrant for the universe. Second law says all things must pass.
The ever-present supply of energy in the universe inevitably becomes more dispersed, more chaotic, and more unusable. Each star burning in the sky, just like each briquette of this charcoal, must one day face its fate.
This piece of charcoal is fuel. It has a lot of energy concentrated into this small little packet here. The energy goes from being in the chemical bonds of the charcoal briquette to being liberated in the form of heat and light. Now, a star does a similar thing. It doesn't burn in a chemical sense. Instead, in a star, it's nuclear energy. The nuclei of atoms are being forced together, fusing them, creating new nuclei, and in the process, transforming some of that matter, some of that mass, into the radiated energy that we see and we feel. And the same process is going on in all the active stars in the universe. Now, as this charcoal is burning, the fuel is getting used up, and you can actually see that. It's turning into a gray color, it's turning into ashes. In a similar way, stars use up their fuel. They fuse hydrogen into helium, and so with time, there's less and less hydrogen to fuse, and the ashes have less energy content and thus are either harder to burn or release less energy during the burning process.
This is the eventual fate of our own sun. As it ages, it bloats and heats.
The Earth will be fried to a crisp. Oceans will boil away, all plants and animals will die, rocks will start vaporizing because the sun will be producing so much light, so much energy. That'll be a pretty gruesome death for the Earth.
All through the universe, stars
placed.
During the latter part of this era, there will always be about 50 stars shining in the galaxy at any one time. And that'll be the last sort of gasp of the kind of world, the kind of planets, the kind of environments that are familiar to us.
As we move through the succeeding cosmological decades, and after the last star dies, we enter a new alien age.
So up here, we're in the cosmological decade 20 through 30. And if we look out at the night sky, it's absolutely, utterly, completely black. But if we're able to look in light that's far too red for the human eye to see, then we would actually see that the sky is speckled with dead stars. This is the degenerate era.
In the degenerate era, the most massive dead stars have collapsed into black holes. But punctuating the total blackness of space, the leftover ashes of once bright stars are still ebbing energy.
To go into the degenerate era, we'll have roughly 100 billion dead stars orbiting each other in a giant elliptical configuration.
Occasionally they'll interact with one another and one will get flung out of the galaxy, causing the galaxy to lose mass. The galaxy, in a sense, will evaporate slowly with time as these things are flung out.
White dwarfs and remaining galactic material fall prey to black holes.
So gradually with time, what'll happen is the galaxy will have fewer and fewer objects in it, and a greater and greater fraction of them will be black holes.
And whatever isn't seized by the millions of black holes roaming the universe begins to decay with old age.
And this is another example of the general process by which the total amount of randomness increases in the universe. The second law of thermodynamics is once again at work.
And all the structures, all of these stars are basically evaporating into nothing. And so by about cosmological decade 40, most of the stuff that's been built, the planets and stars are all gone. And the degenerate era, which is stretched for huge amounts of time, is coming to an end.
With nothing left in their way, black holes stand poised to rule the universe. This may be the grim future of the cosmos. The planets decay and dissolve. Dark galactic remnants scatter across a bloated universe. And even light is just a faint, distant memory. As we continue through the vast stretches of time measured in cosmological decades, massive black holes survive as the only recognizable features of our once brilliant night sky.
We're up to about cosmological decade 60-something, and when you look out at the night sky, it's incredibly cold, it's incredibly black, and there's only the faintest crackle of radio waves and gravitational radiation echoing through the empty skies. This is the black hole era.
The continuous expansion of the universe has taken its toll. The unimaginable cold saps energy and constricts movement. Time itself seems to lose meaning.
In the midst of the black hole era, even the degenerate era looks like the first sliver of time after the Big Bang.
Does life have a chance in this environment?
Humans won't exist at that time because protons won't exist. But it's possible to imagine some kind of entity which is living at an extraordinarily slow rate.
If it lives slowly enough, perhaps strange life could emerge. The real action in the black hole era occurs when two black holes meet. Although invisible to human eyes, a collision between these two beasts sends a shudder through space-time. This event can be imagined in a sheet of perfectly still, calm water.
It's a bit like suddenly dropping a gigantic rock into that calm water, sending out a huge series of ripples. And you have a lot of action for a little bit of time, but then that dissipates, the ripples die away, and you're back to that smooth, glass-like sheet of water.
But even for these kings of the black hole era, time is running out.
And you might think, oh, they'll last forever. But even they don't last forever. because they evaporate very, very slowly with time.
Black holes in today's universe grow larger as they gobble up surrounding matter.
But eventually, far in the future, there will be so little material to swallow that the evaporation rate will start dominating over the rate at which they swallow material from their surroundings. So the evaporation rate proceeds more quickly when the universe is very, very old.
An evaporating black hole does not go out with a whimper like the planets do when they
A
die.
huge variety of particles that haven't been seen for many cosmological decades come spewing into existence and kind of flicker away in a last fireworks-like burst after the black hole is gone.
So after about a Google years or so, and the most supermassive black holes have evaporated away, what you've got left is a vast universe that is really almost entirely empty.
Next, the universe enters the dark era.
Now we're out beyond cosmological decade 100. We're in the middle of the dark era. The dark era, everything that we have now that is familiar to us is gone.
You know that expression, angels fear to tread? That's the dark era. The dark era you never want to go to because everything has crumbled. Not just the sands and monuments to man's folly, but even the atoms themselves have begun to crumble. Even black holes are not possible in the dark era.
If the universe continues to expand forever, it may be that only a cosmic mush of random particles remains.